live pretty soon in a few seconds, and then I'll share my screen. Can you all hear me okay?
Yep.
Cool. Just testing out a new setup. I might actually see if I can get some background music pretty soon in a few seconds, and then I'll share my screen. Very Sydney-centric view of the Sydney Harbour. Hope you don't mind. I just sort of copied your photos from LinkedIn just to save a bit of time. Hopefully that all works for you.
That's fine. I know how that is.
Yeah, it's all good. It looks like I need to fix the saturation on mine.
Yeah. Sorry about that one.
No, that's on me.
Cool. I'll just try this out and see if the audio comes through. Yeah. So Ryan, you're a recent graduate, are you? And you've just recently joined Monte Carlo Data?
Yeah, it's funny. I'm actually not quite a graduate yet. I'm kind of a fake senior right now, taking a year off to work with the company, but I'll be going back for my final year of university.
Yeah, nice.
In the fall. Yeah.
You know, it's always good to sort of get out in the field and make it practical, isn't it?
Yeah, it's been, you know, between the choice of remote school and remote work, Monte Carlo was very well configured for the remote environment already, and so I didn't lose out all too much with that. Yeah.
Have you been enjoying it, Ryan?
It's been a fun, yeah, it's been a fun 7 months or so. I actually realized it hasn't been that long, but it's been great. Team is awesome, and it's my first kind of, you know, longer than 3-month foray into professional life, so quite enjoyable.
I hope it does not scare you away.
No, the team's been awesome. Really fun.
Music coming through, or yes?
Yeah.
Just you know, bit of background music, you know, helps with all the awkward silences and stuff like that. But yeah, pretty much there. It's bang on midday, so we might get underway pretty soon. So I will turn this stuff off and quickly introduce our first speaker, Gian. We might all hop on mute once Gian is presenting, just to help him out there. Yes. Second, let me get myself all prepped up. So, very good. I'll fade this fancy background music and we'll get underway. So, hello, welcome to the data engineering meetup. Obviously, due to COVID-19, we're still sort of meeting remotely. It's a combination of the Brisbane, Sydney, and Melbourne data engineering meetups. We've got a nice photo here of the Sydney Harbour, but you know, we'll mix it up and get a nice photo of Melbourne and Brisbane at future meetups, just to keep it nice and even. But yeah, today we've got a couple of folks from I guess the Bay Area of San Francisco. Correct me if I'm wrong. And I think it's going to be a fantastic meetup. We're going to hear from Gian Merlino, who's the CTO and co-founder of Imply. This sort of, I guess, you know, they've got a, you know, sort of managed service solution for Apache Druid. And he's going to be taking us through the internals of it, the storage and query engine of Apache Druid. So I think that's going to be really cool. Gian also joined us for DataEng Bytes on the second day last year, keynoting for that one. So it's really great to have him back this time around. And then later on, we will be, we've got Molly Vorwerk. Hopefully I've pronounced your surname reasonably well. I haven't butchered it too bad. And Ryan Cairns. both from Monte Carlo, which is a fascinating new, data company, and they're going to take us through the next frontier of data engineering. But anyway, without further ado, Gian, take the stage and tell us a little bit about yourself.
Cool. Hi. Let me just make sure I'm on the right microphone. Can you all hear me okay? Cool. Yep. Great. So today, thanks for the intro. I'm going to be talking about Apache Druid storage and query engine. Let me share my screen so you can see what I'm seeing. Is this visible to everybody? All right, perfect. So we're talking about Apache Druid's storage and query engine. And Apache Druid, for those of you who don't know, I'll talk a bit about what it is. It's a database, an open source database designed for analytics, known for being very fast. And so I'll be talking mostly about why it's fast from a technical perspective. Hopefully, those of you that are looking at this are interested in that kind of thing. If so, then you can expect the next 20 minutes or so to be a whirlwind tour through how analytical databases think about making themselves as fast as possible. And if you're not interested, then just sit tight. There's another talk about something totally different in like half an hour. Okay, great. Let's go to the talk. Okay, who am I? I'm Gian Merlino. I'm a committer and PMC chair at Apache Druid. Like I mentioned, I'm a co-founder at Imply. We are hiring for working on Druid, working on the managed service around Druid, working on Pivot, a visualization application for Druid. So any interest in any of these things, we are hiring. Check us out. You can get cool shirts like the one I'm wearing. What are we going to talk about today? So we're going to cover a bunch of stuff. We're going to kind of touch on each of these topics briefly. A brief intro to Apache Druid. What is it? We're going to talk about the segment concept in Druid. That's sort of the core of how we think about data and how we think about data management. We'll talk about how data servers work in Druid, how a cluster comes together. Then we'll dive back into that segment file format, and then finally talk about query execution. And we'll kind of touch on each of these briefly, and hopefully it's interesting. Okay, what is Druid again? It's a powerful query engine. It's like a cool rocket ship. That's how we think about it. But that's how we think about it when we're trying to be fancy. What Druid really is, if we're being honest with ourselves, it's a calculator. It adds numbers up really quickly. So what Druid is if you have billions upon billions of records in a table and you want to add those records up as quickly as possible, Druid's your thing. Why would you want to do that? Why would you want a giant calculator? Well, the main reason most people want giant calculators is to power OLAP applications. OLAP stands for Online Analytical Processing. I mentioned the app we make at Imply is called Pivot. That's on the left over here. It's a pretty typical OLAP style application. You select attributes you want to dial in on. You switch between visualizations rapidly, change your filters rapidly. The idea is to have a interactive sort of incremental experience with navigating through a data set. Applications like Pivot and also other kinds of applications, BI applications, observability applications are going to be built on data systems like Druid that focus on just being able to add stuff up really, really fast. And that's why we speak SQL. So Druid speaks SQL so you can build your own apps. Druid's used in the wild a lot. I like to have this slide just so, if you're falling asleep by now, maybe you'll pay attention a little bit longer if you see that people are actually using this thing. So that's the purpose of this slide, used by Netflix for real-time insights. Recently deployed at Salesforce for a big new analytical application there, enabling analytics at Airbnb, enabling interactive analytics at Mopub, querying terabytes of data in seconds. Mopub is a Twitter company. And so it's pretty heavily used in the wild, and that is it's great. It's really fun for us. It's fun for us to be able to build stuff that does get used at this large scale, because we like making data software. But what data software is no fun unless you can put data into it. And these are the kinds of people that have that kind of data to put into data software. Some numbers from Imply customers across across the Imply Cloud platform. We mentioned we have a platform called Imply Cloud that is a managed cloud environment for Apache Druid. So across that platform, there's petabytes of data under management, thousands of daily active users, millions of rows per second ingested, and really fast query times. 99% of queries happening less than 2 seconds, 90% less than 1 second. And so this is just to say that we really, really are trying to be as fast as we can at scale, and we're able to do that, and we're achieving it. And okay, so if I've hopefully if I've earned another 15 minutes of your attention, the next 15 minutes we'll talk about how we do this inside Apache Druid. Okay, how many of you are familiar with this beautiful screen grab from the film The Powers of 10? Rhetorical question. I love this film. It's about 10 minutes long. It's awesome. If you've not seen it, go check it out. It's on YouTube. I first encountered it at a science museum as a child, and it stuck with me ever since. It starts with this, hella 70s looking dude lying on a picnic table or picnic blanket in a park. And then it zooms all the way out, power of 10, one at a time, to the known universe, and then zooms all the way in to I think some atom on a DNA strand in his hand, something like that. Anyway, I thought it was a cool concept, and I wanted to use this to talk about the Druid system. So we're going to start at the proverbial picnic blanket, the segment. This is sort of the midway point. So we can zoom out from this and zoom in from this. We're going to start here. This is the midway point. The segment concept is about 1 million rows, 10 to the 6th rows. A segment is a little slice of a table. It's a file on disk. It's a heavily optimized storage format. New segments are created continuously as we ingest data into the system. So when you start a Druid cluster, you're going to have no segments in it. And then as data is loaded, it's going to keep adding more and more and more for every million rows roughly that you add. They're immutable once created, but they can be dropped, replaced, and combined. We call the combining operation compaction, and dropping and replacing can be used for overwriting and deleting data. And they're generally 1 to 5 million rows each. And this is sort of the fundamental unit of storage in the system. The segments have a life cycle. So these segments kind of flow. Data comes in to what we call indexers. It's a kind of server type in Druid. So Druid's a system with a variety of different server types. And the idea is that each of these server types can be individually configured and optimized and tuned. And when you're running in the cloud system, each one has its own instance type that's best for that. Some of them like memory, some like CPU, et cetera. Some like disk. Streaming data coming into an indexer, creating these segments. Those segments get pushed to what we call deep storage as they're built, as they become immutable. So on the indexer, they're getting built up. They then become immutable. They're finalized. They're pushed to deep storage. Deep storage is going to be something like S3, Google storage, some kind of cloud storage. If you're on-prem, it'll be HDFS, or maybe if you're really old school, it'll be a big old NetApp filer. And then that data will be then loaded from deep storage onto what we call historical servers. And historical servers specialize in serving 90% of your data, which is going to be historical, 95%, 99%. Most people's data is historical, and a little slice is going to be the recent data. That's sort of the new segments that are getting built. And so in most clusters, the majority of servers are historicals, and there's some indexers. So this is the basic life cycle. It's an interesting life cycle. It stands in contrast to, I would say, a common design of a lot of other systems where data comes into one server and then stays there. And I just want to talk a little bit about why we do it this way. The main reason we do it this way is to help with elasticity and scaling. So help it when you scale out or scale in the system. We can move, the segments have a very loose affinity to a data server, and so they can kind of move around. And so it helps the system automatically balance when it scales up and down. That's the main reason we do it this way. All right, so let's look inside a data server now. So we're going to do one more zoom level up. We're sort of following this metaphor. We're now at the 10 to the inside a data server level, 10 to the 10th rows. I don't think the 10 trillion on the left is right. I think I messed that up. It should be 10 billion, not 10 trillion. I'll fix it later. We'll fix it in post. So this should be 10 billion rows, 10 to the 10 rows. This is at the level of one data server. So a single data server is generally going to have thousands of segments on it and be able to handle billions of rows. We have a few goals on a data server, design goals of each data server. One goal is on the CPU side. We want to be able to harness all the available CPUs for a single query. So if there's one query happening, we want that one query to be able to leverage the full parallelism of the entire data server. Another goal, though, is to balance CPU use optimally across concurrent queries. So if we have many concurrent queries, we want to have some sort of sense of how do we balance load across those in some sort of prioritization framework. On the memory side, we have sort of similar goals. One is we want to be able to take advantage of high memory hardware. So the more we want to be able to use, we want to be able to have your data set completely in memory if you have the memory for it and take advantage of that and have a data layout that works well when everything's in memory. But when memory is insufficient, we want to fall back to disk. So we want to be able to support that as well. And so the two kinds of data sets we think about supporting, we think about supporting a hot data set. It's going to be about 50, 80% in memory, or a cold data set going to be less than 10% in memory and mostly on disk. And so we think about, when we think about tuning the system, we think about tuning for these two different goals. All right. Oh, nice. Here the text is correct. 10 billion rows. Perfect. So this is what a data server looks like at the 10 to the 10 row level. A single data server has on the bottom here, we have memory map disk, and all the segments are memory maps. It's a pretty common technique used by lazy database programmers like ourselves that don't want to build a disk to memory caching system on their own, because who has time for that? And Linux is pretty good. It works really well. You memory map stuff. It has a page cache. It's great. So we memory map stuff. Linux will put it in the page cache if we're using it. It'll get evicted if we haven't used it recently. And this is the mechanism by which we do caching of the data. The only requirement this puts upon us as programmers is that when we're writing Druid server
Is that me, or does his
operations, so to speak? That I got a message that says my internet is unstable. Are we good? Cool, good. So let's see. There's so that's the disk section. Above that, we have the processing thread pool and processing memory pool. I don't want to, just in the interest of time, I don't want to get into the details of how that's divvied up, but that is divvied up on a per query basis based on, like I mentioned, a priority system. Higher priority queries can access CPUs before lower priority queries, and memory is sliced up such that the concurrent queries are not stomping on each other's memory. Each one gets an allotment that it gets to, an arena it gets to use without worrying about another query taking its memory. And then finally at the top, there's some per query resources, threads that are going to be allocated on a per query basis. This limits the number of concurrent queries we can run. And so this one really important thing we do to protect this resource is we make sure that if you have a lot of, if we make sure there's always some of these per query resources that are reserved for high priority queries. So you won't get a situation where a ton of low priority queries are running and starving out the high priority ones. So that this design generally gets us to be able to achieve our goals. It enables us, we can use every CPU in the service of a single query, but if many come in, then based on those query priorities, we can preempt ones that are running, and we can run a higher priority one instead of a low priority one. And the only thing that we have to do to make that work is we have to reserve a little bit of the per query resources at the top, the thread pool for high priority queries, which is does not mean we need to reserve CPUs, because the CPUs are able to be fully utilized by the queries that are running, even if there's a little bit of space reserved. Okay. There's one more level up. How a cluster comes together. Now we're at 10 trillion rows. This is where that text was supposed to come from, 10 to the 13th rows. A cluster has come together. A cluster can have about 1,000 data servers. That's a very big cluster. Most clusters don't have 1,000 data servers. Some do. Some of the ones on that slide I showed earlier do have 1,000 data servers. A typical cluster is more like 5 or 10. How cluster comes together, we have this process called query fan out. We have these query servers that are stateless. And you can tell they're stateless because there's not a lot of funny pictures in them, and the funny pictures are the state. So these query servers at the top are stateless. They fan queries out to the data servers, and then the results get fanned back in, and that is how all these data servers individually compute their piece of the query, and then they're merged by the query server and then returned to the end user. It taps out around 1,000 servers because at about 1,000 servers, there tends to be enough merging work to do that merger becomes a bottleneck. And at that point, you're probably going to want to have, if you're blessed to have enough budget for 2,000 servers, maybe have 2 clusters. All right, let's see. Should we do questions or should I keep going? What's your stance, Mr. Host?
Yeah, probably just keep going at the moment.
All right, cool.
Yeah, this is deep, man.
Yeah. I hope it's interesting how databases work. All right. If you liked what I was just talking about, you're gonna love the next section. And if you thought what I was just talking about was kind of boring and like not what you're into, then go get a coffee and come back later for the next talk. Because the next section, we are going to go deep. We're going to dive into the guy's hand and look at the DNA. Now we're going to go back to segments. We're going to zoom all the way in and look at the what's happening inside the segments, which to me is the most interesting part. To me, this is where the core performance comes from. Everything I described to you earlier is sort of about distributed system stuff, resource management, which is like all well and good, but I think it's the most interesting stuff is how do we actually lay the data out? How do we actually do a query? So this will be the final part of this talk. I'll give a little bit of flavor of that. Okay, here's the segment format. There's a lot of stuff going on, but it's okay. We'll talk about it piece by piece. So here's a data set with the columns are time, artist, city, price, count. It's sort of like a pre-pandemic, maybe mid-pandemic, if what I hear about what's going on in Australia is correct. It really is like, I don't know. We can talk about that later. But where I'm at, there have not been any concerts in a year of any kind. So this, for me, is a pre-pandemic data set. Also, I'm dating myself a little bit with the musical references. Maybe I'll update them at some point, but for now, they remain kind of early 2000s, late 2000s sort of references. So here's it's ticket sales data set. And let's say what we want to do is, okay, so there's a bunch of timestamps. We store them in epoch times, or milliseconds since the Unix epoch. For the artist section, so I'm going to, a sort of a normal column is this is a string column. The artist column is a string column. There's 3 sections. There's a data section where we store row by row. What are the values? It's dictionary encoded. So the 0 means Justin, the 1 means Kesha, the 2 means Miley. So this is 3 Justins, 2 Keshas, and 3 Mileys. So this is a 8-row segment. It's not a million, but 8's what fits on a slide. So it's 8. So this is an 8-row segment. The number of rows here, the number of rows here are the same. There's a dictionary that tells us the 0s, the 1s, and the 2s. What are they? This lets us interpret the data section. We'll see why these are separate in a little bit. And then there's an index, and the index tells us how to filter on this column rapidly without looking at the data. So let's look at a query. I don't know what this orange box is for. I don't want to talk about it. Let's look at a query. Here's a simple query. We want to look at all the cities, total up the price from this table where the artist is Justin, and we want to group by city. So what we're doing is all the rows that figure out for Justin, how many ticket sales were there on a city by city basis. Relatively simple. A definite sort of add a bunch of numbers up really quickly problem, which is the kind of thing we should be good at. So let's see how we do it. Okay, the first thing we do, and I never understood why SQL is written in this order. why don't you put from first and then where and then group by and then select should be last? I don't know why it's first. It's always confused me. But it was the 70s. It was a crazy time when they designed SQL. Okay, so the first thing we do, where artist equals Justin. So that's the first thing that executes. What we're going to do is we're going to figure out the dictionary code for Justin. Because I mentioned we want to use the index. The index is in the same order as the dictionary, and so we're need to know where to look in the index. So the dictionary is sorted. JKM. It's sorted in alphabetical order. We can do a binary search because it is sorted. So it's a logarithmic amount of time to find the dictionary code for Justin, and that's not a lot of time, which is good. So we know it's 0. Then we're going to the index. The index is going to tell us that the first 3 rows match this filter. So now we know that the first 3 rows are Justin's. We could have looked at the data section to see the first, the zeros are the first 3 and nothing else is a 0. But this way, we didn't have to look at the data section, which is better. The best way to read something quickly is to not read it at all. That's the secret. The secret is minimize accesses. Anyway, we know it's the first 3 rows. We're done with the artist column. The data section is like dead to us. Didn't even have to be there. We are now going to go to the city and price columns and do the group by. We know we only care about the first 3 columns, so we're not going to look at anything else. Sorry, the first 3 rows. So we're not going to look at anything else. We're going to look at the city column. We see a 2, a 1, and a 2. We take the corresponding prices, total them up in a map. This is an in-memory map. The key is the dictionary code for city, and the value is the price that we are incrementing every time we see a new price. So for 2, there's 2 values, 1800 and 1953. We add them together. For 1, there's 1 value, 2912. We put that there. Use the dictionary to figure out the names. Get rid of the null, and then we're done. We've finished the query. And what we've done here is we've done a binary search in the dictionary. We've done a random access in the index for 1 column, and we've read 3 rows out of the data section of 2 other columns, and then 2 values of the dictionary. So we've been very economical with what we've read out of the segment, which is really important. It's really important because that's how things are fast. It's fast when you the fastest thing is nothing. It reminds me of a poster I saw once that I forget what company it was, but it was on the wall. It was the 4 rules of performance, and the first rule was don't do it. I don't remember the other 3, but they don't matter. Don't do it is the most important rule. If you don't do it, it's fast. Okay, that was all I had. If you're interested in a longer version of this talk, you can find one online if you search for the Druid talk at the CMU vaccination database series. It's about twice as long, so twice as much detail on the same stuff. If you just want to try out Druid and don't care about how it works, check out the website, druid.apache.org. Follow us on Twitter, druid.io. And if this stuff is really interesting, then go to imply.io/careers and come work for us. Thank you.
Thank you, Gian. That was a really fascinating talk. We had some good stuff coming through on the YouTube chat. I think some of it was a little bit too sort of in detail for some of the data engineers that we've got. A lot of them are fans of using data warehouses, less so much building them from scratch, and probably even less so much building cutting edge super fast data warehouses. So but that was really cool. I really enjoyed that talk. Just
at least people were at least interested in seeing how some of the tools that we use every day work under the hood. I mean, the techniques that we use in Druid are the same techniques that pretty much every columnar database uses. So stuff, BigQuery, Presto, Snowflake. Under the hood, these techniques are all being used by all these systems. And if it's fun to learn about, then there's a lot of stuff out there to watch.
Yeah, absolutely. It's a bit like getting to understand how your favorite cake was made. This sort of ingredients that get thrown into the mix. So that was really cool.
Yeah, we're actually working on a Netflix show where we kind of go into the details of this stuff.
Master Chef for
exactly. Yeah.
Yeah. Wow. Awesome. Can't wait for that one to come out. And just real quickly, so, Imply, I guess, is, for hot data, like your last year's conference talk was Some Like It Hot, alluding to, the need for, query response times to be super fast. What sort of use cases are you finding out there, talking to your customers, those that you can sort of talk about? Where do people look to use either Apache Druid or Imply?
Yeah, I would say that for me, the ones that seem to be the best fits are there's kind of two that I've seen. One is these sorts of observability use cases where you want to, for historical data, you want to figure out root causes of like stuff that happened in the past. And so you want to be able to drill into things on a ton of different dimensions. And so you don't want to be doing a lot of pre-aggregation. You want to kind of retain highly granular data, but be able to navigate it quickly. And so you need a system like this. And also like real-time observability type stuff where you want to be able to, I didn't talk much about the streaming ingestion in the system, but there is a streaming ingestion component. You can get this stuff in real time as well. So that's a big one. And I think another really, really big one is if you're trying to provide analytics as a service. So like a really big business for us at Imply is working with customers that want to provide analytics to their customers. And so they're looking to provide a portal where their partners, their customers can log in and see, a slice of data that corresponds to their relationship. And, imagine like a video streaming platform that wants to let publishers log in and see details about their video views and how they're performing and audience and all that kind of stuff. So that we do a lot of that. And you might imagine that it is really important to have a system like this that is fast and is always online and all this stuff, because if you're providing a service to third parties, you really want it to be high quality.
Absolutely. So it's kind of like you're enabling sort of like a Google Analytics type capability with, I guess, live analytics of, say, people hitting a website, but for, companies that want to sort of provide that to their customers.
Yeah, exactly. That's how a lot of the business that we have at Imply does start that way, where someone's, I want to offer this to my customers. I want to offer something like Google Analytics, but it's my data, my customers. How do I do it?
Yeah, that's really cool. Fascinating. So Stefan Main, he's asked, so you use intern strings as symbols. Does that mean that you have random strings may actually slow you down?
That's a good question. It tends to not be so bad because I guess you're probably referring to the fact that there's a dictionary, and it tends to not be so bad because, like I was mentioning, these dictionaries are part of a segment that's memory mapped and stored on disk, and so they're not part of. So Druid's a Java system. It's not part of the Java heap at all. It's something that's happening off heap. It's happening in memory mapped files. If you think about it, I guess it's not causing any garbage collection pressure, which is, and it's not causing any memory pressure really. At all, which is usually why the stuff is bad. So it doesn't have those problems. And if you think about it, the structure that we have, if you do, it works really well as a form of compression if you have redundant data, because the dictionary codes are kind of like a form of compression. If you just have random strings such that there is no compression there, then it's kind of no worse than how a pointer would work in like C++, because the dictionary code, you can think of it as a pointer. It's every string has a unique offset that points to that string, and so the overhead is not really much different from that. Oh, I can't hear you.
Sorry, I muted myself and started talking. Usual. I had someone just reversing into their garage next to me, and I was thinking you probably don't need to hear that on the live stream.
Yeah, fair enough.
But yeah, so thanks so much, Gian, for coming by and presenting that to us. Really keen to see what the uptake out there in the community is with Apache Druid and Imply, and what other folks are building with it here in the APAC region in Australia and New Zealand. So yeah, and who knows, we might even be able to get you again for the DataEng Bytes conference, fingers crossed, or someone else, to talk about, some further Imply use cases, because I think it's a really fascinating.
Yeah, it's always a pleasure, and thanks for having me here.
Awesome. Thank you. Cool. So up next, we've got a couple of folks from Monte Carlo. I'm just going to read a few of my notes. Apologies for that. So much going on right now. So many cool new data products being released. But yeah, so we've got Molly Vorwerk. She's the head of content and community at Monte Carlo. And we've also got Ryan Cairns. He's a data scientist at Monte Carlo, sort of mid-degree, but I'm sure he's smart as anything, and he's got a lot to offer today, and it'd be fascinating to hear from him, hear from you both, in fact. And they're going to be talking about the next frontier of data engineering, and really around this problem of data observability. I cannot tell you how many times we've had, talks about, oh, my data pipeline has been broken and I didn't realize till a little bit too late, or something like that style talk at the meetup. So, and I think, what we're seeing in data engineering as it's becoming increasingly popular, this proliferation of data pipelines, also offloading them to sort of SaaS products and stuff like that. But nonetheless, this observability problem and solution, it'll be very fascinating to hear from you about that. So without further ado, please take it away.
Awesome. Thanks for the introduction, Peter. And that was an awesome presentation to follow. We'll do our best. Let me share my screen here. All right, so as Peter mentioned, my name is Molly, and my colleague Ryan will be joining me, and we are on Monte Carlo's team. So Monte Carlo, in a nutshell, is a data observability platform that applies kind of best practices of DevOps and software engineering and root cause analysis to your data pipelines to help you, solve that problem you were talking about earlier, Peter, of, oh no, my dashboard looks wrong. What happened? How do I fix it? So in this talk, we're going to talk about what data observability is, where it came from, and the inspiration behind it. Ryan is going to walk through some kind of real world case studies about how some companies are applying it to their pipelines today. Oops. All right, so a little bit about us. So I'm Molly. As Peter mentioned, I head up content and community at Monte Carlo. Prior to that, I worked at Uber. I ran their engineering blog and helped facilitate some of the tech and brand development things. So if you ever read an Uber engineering blog article or engaged with us on Twitter, I was probably involved in some way. I also freelance for USA Today, which is a large kind of national publication in the US, and I cover history and pop culture, so that's kind of my side gig. And before that, I attended Stanford University. So Ryan, why don't you introduce yourself?
Great, thanks Molly. Hi everyone, my name's Ryan. I'm working in data science, data engineering at Monte Carlo. I'm actually technically a senior at Stanford right now. I took a year off for the past academic year to work for Monte Carlo for the last 7 months. Very happy that I did. And before this, I've worked a little bit for GGV Capital on Sand Hill Road and Afterpay in San Francisco, where I did some software engineering there. And yeah, calling in from Palo Alto, California. Very excited to be here.
Awesome, thanks, Ryan. All right, so let's get started. So I'm sure a lot of you will be familiar with a lot of the principles that I'm talking about today. Application observability and DevOps is probably not unfamiliar to you. So, as you're likely aware, in the 2000s and 2010s, engineering systems at companies like Google, Facebook, Netflix, Uber were growing increasingly distributed, increasingly complex. These companies were building and digitizing enormously, and they needed a way to understand the health and performance of their applications as they scaled. So they needed tools to basically tell them, okay, why is my website down? If it's down, what's the cause of it? Who's affected by it? And so a lot of really exciting tools were built, many of them open source. So I know at Uber, one of the tools we built was called Jaeger, and it was a tracing tool. And so it's just it was a very exciting space to be in, and it really helped software engineers kind of understand what was going on in their systems in the back end so that they can continue to deliver performance and fast and accessible services. And so, I tell this to everyone, but if you're just getting started in SRE, if you have not read Google Site Reliability Engineering Handbook, please do. You will thank yourself later. It's a really great kind of, it's a great tutorial in understanding just site reliability engineering from end to end. And it gives a lot of really good practical tips, not just for rolling out the tech and doing things from a technical perspective, but also organizational structure, communication, collaboration, just generally best practices for getting people to understand why observability and reliability is important, because often it doesn't get enough love because people don't find it super interesting, or not interesting, but super you're not building a new product, you're keeping products performant. So it's a little bit different, but it's very important and very exciting. All right, so in observability, which is basically kind of the way of understanding the health of your system at any given time in a distributed architecture, there are, various ways that things can go wrong. And so there are three key pieces of data that we can use to understand the health of your application at any given time. So it kind of splits up into logs, metrics, and traces. So for those unfamiliar, logs are structured and unstructured lines of a text that a system produces when certain code runs. So a record of an event within an application. Metrics are a numerical presentation of data that can be used to determine a service's behavior over time. So metrics comprise a set of attributes that convey information about SLAs, which are service level agreements, SLIs, service level indicators, and SLOs, service level objectives, which are all kind of frameworks for understanding or measuring the performance of your system. Often companies, they have certain agreements with their customers, like we'll have, 5 nines of uptime, or we'll only have 1 hour of downtime per quarter. I'm sure you guys experienced Slack's, famous outage, or not famous, but in January, Slack had a major outage, and it was the outage heard around the world. And it's actually funny. My fiance is a site reliability engineer at Slack, so he was involved with that. Anyway, so very, very important tools to help you understand the health of your system. And one thing to point out is that observability really is different than monitoring. And monitoring is a way to kind of consume information passively. Folks can ask questions based on dashboards built to maintain kind of static environments with little variation. And then observability, on the other hand, is kind of a way of gaining understanding more actively. It's like putting the pieces together to understand what went wrong and what you need to do to fix it, versus just, passively, alerting you if something happens. So observability often combines much more tooling and integrations. A really awesome voice in the space on observability is Charity Majors, who is, I believe, either the CTO or CEO of Honeycomb, which is an application observability tool. Highly recommend following her on Twitter. You will not regret it. All right, so that being said, I'm going to pass it over to Ryan to talk a bit about how all these concepts and principles can be applied to our data pipelines.
Great, thank you, Molly. Yeah, I think that Molly's introduction with application observability as the focus is a really interesting way to frame this discussion on data observability. There is kind of this pattern that I think is worth highlighting here, in that pioneers of the application observability space kind of started in kind of the FANG level scale of companies, and then that kind of terminology gradually democratized, and now you can pretty much have any modern tech company talking about site reliability engineering, hiring SREs, defining the sorts of SLIs and SLAs that Molly discussed. It's really kind of broadened in scale. And I think that data observability is sort of following the same trend. If you can infer from that, you may expect to hear whispers of this concept at the kind of FANG level enterprise scale. And that is indeed what we're seeing. So I've got a couple examples here that I think are interesting from very large, very pioneering companies in the space. The first is Netflix. Netflix has this talk from 2019 that I really recommend, where they experienced a 40-minute outage of their entire application. So both as an engineer and a Netflix consumer, 40 minutes is a long time. This is an issue that they caught that was difficult to diagnose because no code had been pushed to explain the recent outage. And so all of the kind of orchestration of tools that they had built for catching a change in the code, all of their kind of CI/CD pipelines, the unit testing, code review and revision, and provenance, and all of those things weren't up for fixing this issue. And they noticed this, and in the talk they kind of talk about this as the paradigm shift for them, realizing that changing the data is as influential to our application's performance as changing our code. What had happened was a batch of data had come and duplicated, and they'd built application code that wasn't configured to deal with duplicate values, caused the whole system to kind of cascade in failure, and was down for nearly an hour. So after this, the course of the talk, Netflix talks about building Canary, which is their end-to-end real-time anomaly detection service for their data, which performs data validation across Netflix services. It's a very interesting technical talk that I'd recommend. Kind of moving on to Airbnb, another sort of giant in this space. Airbnb, I remember being kind of very enthusiastic about the adoption of Facebook's GraphQL. It was released open source in 2015. So they have kind of a very multidimensional, complex data environment. And they've scaled rapidly, of course. The volume of their data assets has grown really considerably in the last, say, 4 years. And so there's a sequence of 2 blog posts that Airbnb engineering has, where they talk about their system called Midas, which is sort of defining the gold standard for data quality at Airbnb. And they do some really nice work kind of defining some terminology here that I think is motivating, talking about the timeliness of data, the accuracy of data, the sort of availability of data provenance, and the history of the pipeline. I think this was another kind of interesting piece of literature describing how data observability is sort of starting to come into form and have a definite vocabulary for working at these high scales. And a last example, Uber, of course, an enormous data-driven business. They schedule 14 million rides per day, I think. And so the nature of Uber's system, working with petabytes of highly complex structured business logic and data, they published a very in-depth account talking about the in-house tooling they've built here. Specifically, sort of interesting contributions, taking the most modern techniques in big data and machine learning to sort of apply dimensionality reduction and do all sorts of very interesting time series anomaly detection to ensure data quality at Uber. And also a bit of discussion on sort of the terminology, starting to use those terms, observability, more and more frequently. And so I think this is a good intro. I think this space is sort of come into being a little bit. A lot of pioneering companies are discussing it, and I'll hand it back to Molly, who's gonna have some interesting stuff to say, kind of formalizing the concept of data observability.
Yeah, thanks, Ryan. Yeah, so as Ryan mentioned, a lot of these FANG companies and others are really embracing looking at data in a holistic end-to-end way to understand, when issues arise, what happened and how can we fix it quickly so that the decisions and the services that are powered by our data can go back up and running, and data engineers don't have to spend hours firefighting. So Monte Carlo kind of has been writing a lot about this topic, data observability. And so we actually spoke to over 200 data engineering teams in the past few years, trying to understand what their biggest pain points were. And so time and again, this issue of what we call data downtime, which is essentially just your broken data pipelines, duplicate values, null values, anytime your data cannot be trusted or is unreliable for some way. And so time and again, the companies that we were talking to cited this as one of the top sources of frustration and pain. So if we go back to definitions of application observability, basically as a way to automate away toil, we can apply that directly to data. So ways to automate and kind of remove the toil in a data engineer's life. One main source, obviously, is bad data. So what we were finding when we were talking to these companies was that not only was this tedious firefighting data pipelines and time consuming, but people were losing revenue to the tunes of millions of dollars per year. There's actually some statistics, I think Gartner or something posted it, but it was like 1 in 5 companies have lost a customer due to bad data. So it's not insignificant. And then another one is erosion of trust in the data, both internally and externally. If you can't trust your data, then what ends up happening is people having duplicate data sets. Some they trust, some they don't. They don't know where it lives. They don't know who owns it. They don't know if it's being updated. And it's just very hard to keep track of everything. So in this way, observability can be fundamentally important to the success of any data team. And so what it does is kind of codify a way of understanding this problem. In this definition, it refers to an organization's ability to understand the health of the data in their system at any given time, essentially eliminating this problem of data downtime. And so like in DevOps, data observability often applies some measure of automation, which Ryan will talk a little bit about later, alerting and triaging to identify and understand data quality issues and discoverability problems as they happen in real time. Similar to the concepts of three pillars of observability, we've kind of put together 5 pillars of data observability, including freshness, distribution, volume, schema, and lineage. So all these terms will probably be perhaps too familiar to you on a day-to-day basis. To start, freshness is kind of one of the things most people complain about when their data is wrong. Why is my dashboard not up to date? Data, as we know, data pipelines can break for millions of reasons, and freshness is often at the top of the list. Freshness is this idea of, is my data up to date? What is its recency? Are there gaps in time when the data has not been updated? And do I need to know about that? Among many other questions. A second pillar is distribution, which relates to your data assets field level health. Null values are one metric that a lot of people use to understand distribution at the field level. For instance, if you have a particular field, if you expect a certain percentage of null rate and then you suddenly have a spike in a very significant way, like that may indicate a distribution issue. And so in addition to null values, other measurements of a distribution change include abnormal representation of expected values in a data set. So that's another one. Third pillar is volume. So literally it just refers to the amount of data in a file or a database. And it's one of the most critical measurements when you're trying to understand if your data intake is meeting expected thresholds. So volume refers to the completeness of your data tables and gives you insight into the health of your data sources. So if 200 million rows suddenly turns into 5 million, you should probably know about it. And so it's a good metric to have. The fourth is schema. And so having spoken to many data engineers, I know schema changes are one of the #1 causes of broken pipelines. So schema, for those unfamiliar, is structure described in a formal language as supported by a database management system. So oftentimes we find that schema changes are the culprits of broken pipelines. Fields are added or removed, changed, tables are removed or not loaded properly. And so auditing and kind of monitoring this and having, a strong understanding of when these changes are happening and who's been affected is very important to understanding the health of your data. So the final pillar here is lineage. And in a lot of ways, this is one of the most important and most holistic when it comes to doing root cause analysis on your data pipelines. And so lineage kind of helps us put everything together. And it helps us paint a picture of what your data ecosystem looks like at any given point in time. In fact, when data breaks, the first question most people have is, where did this break? So data lineage provides the answer by telling you which upstream sources and downstream ingestors were impacted, as well as which teams are generating the data and who is accessing it. Good lineage also collects information about the data, referred to as metadata, that speaks to governance, business, and technical guidelines associated with specific tables. So it kind of becomes a single source of truth for all consumers. So lineage helps us tell a story about the health of your data. For instance, upstream, there was a schema change that resulted in a table downstream that had a freshness issue that results in another table downstream that had a distribution problem, so on and so on and so on. So in a nutshell, those are the 5 pillars of observability. And now I'm going to kick it back to Ryan to kind of talk about how this comes about, like in the real world for a lot of kind of cutting edge data teams. I'll skip through root cause analysis here. Oops, sorry. One sec, having issues with the deck. Okay. Weird. Okay, I will just make the slide big and you can hopefully see it. One moment. Oops. Okay.
Might even be worthwhile just refreshing the page. Sometimes I find these browser-based things with the yeah.
Let me do that. Okay. There we go. All right, sorry about that. Here we are. All right, Ryan, take it away.
Perfect. Awesome. Yeah, so when I kind of contributed earlier in the talk, I had sort of big names in mind, the Netflix, Ubers, kind of enormous scale companies. Then I also talked about that democratization effect, the way that, now an SRE is a recognizable job title at pretty much tech companies of all scales. And so I think that this trend is replicating itself in the world of data observability. And I'm very excited to kind of talk through a couple success stories we've seen with younger data teams doing really cool cutting edge stuff, championing data observability and kind of seeing the benefits of it for the data engineers and for their product and company as a whole. The first of those is Blinkist. For those not familiar, Blinkist does this pretty cool subscription service for book summaries, basically, providing sort of audio snippets to allow you to kind of preview a whole bunch of different books without investing your time outright in those. Naturally, as I think people on many different data engineering teams can attest, this is a product that's very affected by trends from the pandemic. And so what happened at Blinkist was a lot of the historical trends they had been using to track marketing spend and correlate it with user behavior were suddenly no longer standing up. So there's deviations from the historical trends as to how their marketing spend can sort of predict consumer behavior. And this sort of caused a lack of trust in the data systems and the pipelines that were reporting these metrics, sort of eroded trust in the pipeline and in the reliability. And so kind of to combat this, Blinkist champions data observability. They've embraced it and used it to sort of course correct, understand the health of their data in light of major historical events, changing trends. They've sort of come a long way to really embodying this practice. They have dedicated data reliability engineering dashboards, tools, team members who spend a lot of their time working in this stuff. And since sort of starting to champion this last September, they've seen a 40% growth in marketing ROI. So really impressive, sort of flexible navigating, despite everything that was going on in the world, to sort of get a better sense of their data pipeline and use this this practice to their advantage. Yeah, another cool example is the farmer's dog. This is a small data team. They, like Molly kind of alluded to, Farmer's Dog has been super excited about the sort of opportunities for automation that happen within a fully fleshed out data observability environment. So sort of similar practices to SRE and to the DevOps space in general, where you really try to automate away manual toil in the build and deploy process. And so not only has this reduced the time to detection and time to resolution, but significantly lifted the burden of work. If you think back to the pillars that Molly was talking about, for example, freshness. If you just have a timestamped field in a database, you can use that column of data to start running some time series anomaly prediction just straight out of the box, even in plain SQL, and start to see some results detecting anomalous differences in say, time deltas. That's just one simple example. Obviously, schema changes can be automated if you're reading from your metadata stores. You can even sort of do some sort of interesting aggregations and start detecting anomalous spikes in null rate. Suddenly, the whole world of time series anomaly detection and the modern ML toolkit comes into play. Yeah, Farmer's Dog is a really good example of a team that has been able to kind of operate with a higher level of maturity due to their skill at implementing this automation. Lastly, kind of on the other end of the startup side, Yotpo is an interesting company. They've got a data team of around 25 people, which is that sort of, it's the precursor to kind of a high rate of scaling when you've got different data scientists and engineers and analysts all kind of working with the data from different vantage points. And tribal knowledge starts to take over at that scale, where now you need to kind of get a sense to sort of penetrate the fog and say, what do all these different tables mean, and what is actually going on with this pipeline? Who's querying this table? Who's loading into this table? At these scales, communication and end-to-end comprehension is key. And data observability, especially the lineage capacities that you can build in, really allow you to sort of figure out, when something breaks, what is it impacting downstream? So what will my production dashboards look like as a result of this outage? And then also upstream, if I want to look at the root cause, is there a schema change 3 or 4 ETL steps back that might explain the reason for this table's lag in data? It hasn't updated today. Maybe this is because of an upstream issue. And we've seen this to be super effective with teams that are aggressively scaling and hiring, being able to provide a catalog, provide data discovery, and sort of operationalize those again at high scale. So that hopefully is kind of a whirlwind tour that will convince you that this is no longer a space just for FANG. This really is a space that's dynamic, it's democratizing. Lots of cool new work is going on. And just to kind of conclude, if I could bring up, maybe 4 key takeaways for designing an end-to-end approach. There is this notion of setting baseline expectations, what good data looks like. This was especially apparent if you go back and read those Airbnb blog posts. They are really keying into this idea of, okay, what can I expect if I have certified data? That needs to be timely. It needs to be viewed in context within a pipeline. and so forth. That kind of moves me to the second point, monitoring across the 5 pillars, data observability, this sort of explicitness. I think this space is interesting because a lot of the sort of innovation has been in the terminology, in the clarity of thinking, and not so much in the latest, greatest deep learning or crazy research-oriented machine learning stuff. It really is just kind of a change in perspective. Also kind of key to the sort of real-time detection and scale that we're discussing, collecting and applying metadata, really weaponizing your metadata to get a sense of the different pillars and how they are working in your system. You know, freshness and schema and lineage are really, they're all not possible unless you have the correct metadata to contextualize your data sources. And then lastly, you know, lineage, like Molly said, is sort of one of the most important pillars, if not the most important pillar, because like I said, back with the example with the farmer's dog, you know, correct lineage tells you not only what's downstream affected, what is, you know, going to be impacted in production, but it also lets you move upstream and work towards some very interesting, complex root cause analysis that can drastically reduce time to resolution for some of the nastier incidents, like that one we talked about with Netflix. So it's a cool new space, it's a dynamic space. There's a ton to read and to explore here, and we've provided this list of links. Hopefully this can be made available. I think Molly will make this available in some capacity.
Yeah, we can. It'll be, yeah, they'll get a recording and they'll be able to check it out.
Great. Yeah. So yeah, a lot of recommended reading, I guess. And lastly, if you want to get in touch, these are the email addresses, and of course we're hiring as well.
Yes, we are hiring. If anyone's interested in working on this problem at scale, please let us know. But yeah, as Ryan said, thank you very much. If you're interested in learning more or reading any of our blog posts, just go to montecarlo.com. But thank you for your time, and it was a pleasure to talk.
Yeah, well, thanks so much. Actually, big round of applause both to you, Molly and Ryan, and also to Gian before. Really cool talks. I guess, you know, I was having a little sticky beak at your website, the Monte Carlo data website, and, you know, just looking at the integrations that you've got in regards to, say, you know, you've got obviously data warehouses, but you've got things like DBT and, you know, then you've got Looker and Tableau and things like that. So in terms of your data observability and lineage tracing and stuff like that, does it allow you, I guess, to sort of do that old, here's my end dashboard and here's all of the transformations that I've done in my warehouse, and perhaps even some of the source systems, because you've got things like Airflow and stuff like that in there. Tell us a little bit about your solution, perhaps.
Yeah, absolutely. I can do the high level overview, and then I don't know if Ryan wants to go into more detail, but Monte Carlo actually is entirely end to end. So as long as you are on the cloud, we can support it. So it goes like from your source data all the way to your dashboard. So that includes your warehouses and your lakes, your transformation tools, your analytics tools, and anything in between. So we do support the entire stack, and that's kind of what makes data observability as a principle interesting, because it gives you a holistic look at your entire system. Ryan, is there anything else you want to add there?
No, that's about it. I think, yeah, the ability to get that information in the same place on the same pipeline view is super useful, even in my own work using the own product. So
yeah, I can imagine. And do you find that, you know, like, you know, say, you know, without revealing all of your customers and stuff like that, you find you're working with a lot more sort of enterprise customers, or are startups sort of saying, you know, hey, can I get a bit of help with this one as well?
Yeah, I think because, you know, I think because companies are ingesting so much data, particularly third-party data, and a lot of these companies are short-staffed, frankly, when it comes to data engineering. I mean, it's like the hottest job right now, and there's always a lack of data engineers at any company. So a lot of teams are finding that having like a bespoke kind of centralized solution can be quite helpful. That being said, there are like awesome open source tools in the space and some great things that are cropping up to kind of tackle these different elements of your pipeline versus kind of a more holistic look. And that's great. So we really work with like anywhere from, I think like 1 to 5 people on your data team upwards to, 25 to 50. It really varies.
Sounds awesome. Yeah, well, so I'll just quickly check the live stream just to make sure I haven't missed any questions. No, it looks like we're all good. But yeah, I'm really fascinated. It'd be great, both for Imply and Monte Carlo, that, if anyone out there is actually using these products out there in the wild, just to sort of come back to the data engineering meetup and perhaps do a presentation, because it really is, love these product talks because they, we get to sort of understand a bit of the reasoning and the rationale for why you would kind of take on one of these products or something like that. And let's face it, without turning the meetup into a sales pitch, there is a lot of value just getting a managed service or, someone to sort of tackle a few of these sort of, I guess, undifferentiated heavy lifting seems to be a popular term out there in the market. So, potentially, I think it's really good value. One other sort of last little sales pitch that I'll quickly do, not that I get any commission for ticket sales or anything like that, but I just find Data is a wonderful conference. I've personally got a lot out of it. It actually, when I went to a Data, it inspired me to start this data engineering meetup because I just felt, like there's lots of data science stuff out there, but there wasn't really a good group for discussing data engineering related talks. So definitely highly recommend you get along to this. Tickets are only $129. They're on sale now. I think the actual event's happening on the 12th and 13th of May. Going to be really good fun. Michelle Playfair, who's a director at Yao, she's been a really great supporter of the meetup. So I just couldn't recommend them more highly enough. And I think they might have Zamak Degani again, so talking about data mesh this year. And I think Simon Aubrey, one of the co-organizers of the data engineering meetup, he's also speaking. So should be a good lineup this year. And of course, DataEng Bytes is coming back at the end of August this year. So stay tuned for a few announcements on that. But yeah, I'll just probably sort of do a wrap up here and leave it there. Thanks once again, Molly and Ryan from Monte Carlo Data, and of course, Gian Merlino from Imply Data for joining us. 2 fascinating talks. It's one of the silver linings, I guess, from COVID-19 is we get folks from San Francisco and the Bay Area in California joining us to present some really fascinating stuff. So I guess, that's one positive we can take out of it, right?
Yeah, for sure. I
like that too.
Yeah, cool. Well, see you all next time. And thanks once again.